Greenberg from McGill University. He's going to talk on computing Heegner points arising from Morphic.
All right. All right. I'd first like to thank the organizers very much for inviting me to give these talks. And what I'm going to be talking about is very much related to what Henri's been talking about for the last few days, about Heegner points and how he's been talking about Heegner points and how they influence the arithmetic of elliptic curves and even control it in some cases. What I'm going to talk about is how to really compute these important points in practice, how you can really get your hands on them. And I'm going to be discussing p-adic aspects of this program and p-adic algorithms for computing Heegner points in practice, which arise from Shimura curve parameterizations of elliptic curves. But I'd like to start with sort of a fairly detailed review of what's been going on in the last few lectures, and in the last few of Henri's lectures, and also a bit of stuff that was said in John Voigt's lecture yesterday afternoon. Let me just begin by recalling the classical situation. So let's suppose we have an elliptic curve E over the rational field of conductor n. Then we have a modular parameterization, let's call it phi sub n, from the modular curve x naught of n to E. This is a dominant morphism. It's defined over Q. And we can assume that the infinite cusp gets sent to the origin of the identity element of the elliptic curve. Now, we have a very nice formula for this parameterization if we look at complex points. If we let tau be in the upper half plane, and we let p be its image in the set of complex points of this modular curve, then the image of tau under phi n, to get it, what you do is you integrate the new form attached to E from infinity to tau, and then apply the Weierstrass uniformization. And this, so you have a very nice formula for this, and you can even compute it by computing enough Fourier coefficients of the modular form f sub E, which you can do by counting points on the elliptic curve E and then using the Euler product to fill in the non-prime values. All right, so in particular, this gives us, at least for the classical case, an efficient way to compute Heegner points, which are by definition the images on E of Cm points P in x naught of n of C. These Cm points we met yesterday during John's lecture. Let me just briefly recall what they are again. So the modular curve x naught of n classifies isogenies A to A prime of elliptic curves whose kernel is cyclic of order n. And we'll call a point C, a complex point on x naught of n, a Cm point, and we'll say that P has Cm by a quadratic order O if both A and A prime have Cm by this same quadratic order O. And let's just always let K denote the fraction field of this order O. And in this case, if P is a Cm point, then it's actually defined over the ring class field attached to the order O. And the Galois group of this ring class field over K is canonically, via the reciprocity map of class field theory, equal to the Picard group of the order O. So this is a very nice situation to be in. Now, what would be very nice to know is, when do these Cm points even exist? When do we have these points on the modular curve that are algebraic, that we can project via this modular parameterization defined over Q to get a systematic construction of algebraic points on elliptic curves? And the answer to this question is called the classical Heegner hypothesis. So let's let O be an order in the imaginary quadratic field K, whose discriminant is prime to the conductor n of our elliptic curve. Then one can show that there exists a point on x naught of n with Cm by O if and only if all primes dividing n split in the field K. Now, this is a fairly stringent hypothesis, and it would be very nice to have an analogous systematic construction of algebraic points defined over class fields of imaginary quadratic fields which don't necessarily satisfy this particular brand of Heegner hypothesis. Not only that, we'd also like methods to compute these points in practice if possible. And actually, this is possible, but this generalization requires enriching our source of modular parameterization. We have to allow uniformizations of E by certain Shimura curves. Curves of this flavor John was talking about yesterday and Henri was mentioning this morning. So let me talk about Shimura curves over Q, first of all, because this significantly simplifies the presentation. Now, let's from now on assume that n is square-free. This is a very convenient assumption. And let's let n plus n minus be a factorization of n in such a way that n minus has an even number of prime factors. For the moment, let's even allow 0 prime factors. And let's let C be the unique quaternion algebra over Q ramified precisely at the primes dividing n minus. Now, in particular, this is an indefinite quaternion algebra. It's split at infinity, so we can fix an identification I sub infinity of C tensor R with a set of 2 by 2 matrices. Let's let S be an Eichler order in C of level n plus. Just briefly recall what this creature is. Yesterday, John was working with maximal orders, but I want to add some level structure. So an Eichler order of level n plus is a subring S in the quaternion algebra, which is free of rank 4 over the integers as a Z module. And in particular, if you look at its localization at L for primes dividing the level n plus, this looks like matrices whose lower left-hand entry are divisible by L. So it looks like sort of a congruent subgroup for the primes dividing the level, which is sort of what you would think it should look like. And this is for L dividing n plus. And for primes not dividing n, it's just a full matrix group. Yeah, C splits at L. I'm fixing a factorization n equal into n plus and n minus. The ramification locus is exactly n minus. So at all the primes of L, it splits. All right. So think of S as some sort of analog of a congruent subgroup. And let's set gamma n plus n minus to be the set of essentially units in this order. So let's let it be the image under I infinity of the set of all elements of S whose images have determinant 1. Or said another way, elements of S whose reduced norm is 1. And this sits inside GL2 of R, actually SL2 of R. Now this group, gamma n plus n minus, acts discontinuously on H and has quotient, which will denote x sub n plus n minus of C. And this is compact exactly when there's some ramified finite place, exactly when n minus is not equal to 1. All right. Now one can define a space of modular forms on this group exactly as in the classical case, just the transforms to the factor of cz plus d squared. And this comes complete with a Hecke action, which can be defined exactly as in the classical case, n minus equal to 1. Let me just leave it at that. This can be done. Now, by the modularity of E, together with the Jacquet-Langlands correspondence, there exists an eigenform GE, G sub E, in this set of modular forms on this group gamma n plus n minus, whose system of Hecke eigenvalues matches the system attached to E. As well, and not only that, we also have a holomorphic modular parametrization, phi n plus n minus, parametrizing E of C by the Jacobian of this set of complex points of the Shimura curve. And actually, the way I write it here is mapping the degree 0 divisors on the upper half plane to E of C. This factors through the Jacobian, and it's given by, again, integration against the modular form and then applying the Weierstrass parametrization. Now, when n prime equals to 1, and exactly then, G has a Fourier expansion, in which case we actually have a nice formula, like we saw before, for this parametrization, in which case we can compute it. But when n minus is not equal to 1, when the corresponding Shimura curve is compact, we have no cusps, we have no Q expansion, we have no real way of getting our hands on this holomorphic modular form G. So, and this is the, yeah. One more time? Yeah. What the Jacquet-Langlands correspondence says is that as Hecke modules, if you look at S2 of gamma naught of n, and you restrict to those that are new forms at n minus, at this ramification locus, then this is isomorphic to what I called S2 of gamma n plus, n minus. And you shouldn't think of this isomorphism as being canonical. It's not normalized. What it really is it's a statement saying the same systems of Hecke eigenvalues occur in this module as in this module. So that's what it says, and I'm saying pick something here in the one-dimensional subspace corresponding to the modular form here corresponding to the elliptic curve. So that's as good as we can do in this case. We'll look at some normalization issues later when we look at the p-adic manifestation of this of the Jacques and Langland's correspondence. All right. So as we saw earlier, in the case where we have cusps, we can compute these things classically using Fourier expansions. So what I'd like to focus on from now on is the case when n minus is not equal to 1, when we actually have a compact curve. Now, in this situation, Shimura proved the following. He proved that this Riemann surface that I denoted xn plus n minus of C really is a set of complex points of a curve xn plus n minus defined over Q, justifying the weird sort of notation I chose for this Riemann surface at the beginning. And moreover, this is a moduli space. This curve classifies abelian surfaces in quotes with level n structure. I put that in quotes because I'm not going to bother making that precise, whose endomorphism rings contain this, this order S. Now, there's also a CM theory for these Shimura curves. So if we let O be an order in an imaginary quadratic field, and we let Cm of O be those points on xn plus n minus of C, be those points on this Shimura curve, which correspond to abelian surfaces whose endomorphism ring contain O as a subring commuting with S. So you have O tensored with S injecting into the endomorphism ring of this elliptic curve. In this case, and what the CM theory and the Shimura curve shows is that this set Cm of O is actually contained in the points of xn plus n minus, which are defined over the ring class field attached to O, exactly as in the classical case. Now, this parameterization phi n plus n minus is also defined over Q. So if we look at the image of the Cm points under this parameterization, we get points on the elliptic curve defined over the ring class field. Yeah? Yeah. The level structure, yeah. S is the level structure, right? S is the congruent subgroup that gives the level structure. All right. Anyway, so the image of these CM points under the modular uniformization are all rational over this ring class field HO, and I'll call these curves, these points, Shimura Heegner points to distinguish them from the ones occurring from the classical modular parameterization. Now, when do these exist? When are these sets Cm of O not empty? So let's let O be an order in the imaginary quadratic field K, whose discriminant is prime to n, again, and what we have in this case is a Shimura Heegner hypothesis. Then what we have is that there exists a point on xn plus n minus with Cm by O, by this order O, if and only if all the primes dividing n plus are split in K, and all the primes dividing n minus are inert in K. So this gives some sort of strange conditions on the factorizations of n plus n minus and the existence of Heegner points defined over class fields of certain quadratic fields. What's going on here? What's the system here? Which quadratic field should we expect to get Heegner points from which Shimura curves? And the philosophy that's guiding this it involves the L functions of the elliptic curves. So let me introduce some very non-standard terminology, which I'm just introducing to make the next sentence more comprehensible. If the Shimura-Heegner hypothesis, this above lemma 3, is satisfied for the maximal order O of k, let me call n plus n minus k a Shimura-Heegner triple. I'll never use this terminology again after this slide. Then there exists a factorization, n equal n plus n minus, such that n plus n minus k is a Shimura-Heegner triple exactly when the sign in the functional equation of the L function of e over k is minus 1. And what this really says is that we have a Heegner point type construction, a systematic construction of points, algebraic, over class fields of these imaginary quadratic fields, exactly when the BSD conjecture predicts that the rank of EFK should be positive for some systematic reason. Systematic positive rank, systematic Heegner point construction. That's sort of the one way of looking at it. Nothing rigorous, really. So not only can we play this game over Q, but Shimura curves also parameterize elliptic curves defined over certain elliptic curves defined over totally real fields. For simplicity, I'd like to restrict to the situation of real quadratic fields. In particular, it's the only case I wrote any code for. So the phenomenon of elliptic curves being parameterized by Shimura curves generalizes to elliptic curves over totally real fields in certain cases. And for simplicity, I guess I already said this. Let me let the infinite places of our real quadratic field f be sigma 1 and sigma 2. And let me let P be a finite prime of F. Now take C to be the quaternion F algebra ramified precisely at P and at one of these two infinite places, say sigma 1. And let's let S be a maximal order of C. And we can fix an isomorph, because C is split at sigma 2, we can fix an isomorphism of S tensored over sigma 2 with R, an isomorphism of that with the 2x2 matrices. And let's let gamma contained in SL2 of R be the image under I sigma 2 of the group of units of S of reduced norm 1. Same as before. As above, the quotient gamma mod H is a compact Riemann surface. It admits a moduli description and a corresponding CM theory. And so let's take F in S2 S2 of gamma naught of P to be a Hilbert modular new form with rational Hecke eigenvalues. Then in this case, an appropriate version of the Jacquet-Langlands correspondence and an appropriate version of the Eichler-Shimura construction assert the existence of an elliptic curve E over the real quadratic field F parameterized by the Jacobian variety J of this Shimura curve X, corresponding to this order in a totally real field, in a real quadratic field. And moreover, what we want, of course, is the elliptic curve's L function to match the Hilbert modular form's L function. And this, in fact, happens. And again, we want to compute the images on E of the degree 0 CM divisors on this Shimura curve, on the Shimura Jacobian J. And this will give us points algebraic over certain class fields of CM fields. So the question is, how do we efficiently compute this modular uniformization phi n plus n minus, and hence Heegner points when n minus is not equal to 1 and the formula star, which involved the Fourier coefficients, is not available? And what about E when E is defined over a real quadratic field? These are the computations we want to do. Some work has been done in this before. Noam Elkies, at a previous algorithmic number theory symposium 8 years ago, developed some methods for performing these computations in certain cases in using Archimedean analysis, where he used specific presentations of the groups gamma n plus n minus. And this is very much related to what John was talking about yesterday. But what I'd like to do is I'd like to present an approach based on p-adic analysis, and our main tools will be the Teoretic-Grinfeld theorem, p-adic integration, and the theory of rigid analytic automorphic forms on definite quaternion algebras. The first two are things that Henri was talking about this morning, and I'll review them briefly again. And rigid analytic automorphic forms, this I'll introduce in due course. All right. So earlier, this morning, Henri introduced the p-adic multiplicative integral. Let me just recall its definition. Let me let Bn be the standard decomposition of P1 of Qp into P to the n plus P to the n minus 1 balls of radius P to the minus n. Let mu be a p-adically bounded z-valued measure on P1 of Qp. And let f be a continuous non-vanishing function on P1 of Qp. Then we can define the multiplicative integral of f against mu by taking Riemann products instead of Riemann sums and looking at the limit as the radii of these balls go to infinity. And this converges, no matter what points tu you choose in your representative balls u, because of the hypotheses that I imposed here. Here, of course, it's essential that because we're exponentiating, we need this measure really to be z-valued. Otherwise, there's ambiguity. All right. Let me let mu sub e be the z-valued measure on P1 of Qp corresponding to E, whose construction Henri described this morning using the p-adic boundary measures and the Teoretic-Grinfeld uniformization. But one can also construct this measure mu e without any p-adic uniformization theory using Eichler's trace formula. But of course, the p-adic uniformization theory will be essential for all our computations. Now, for the rest of the talk, let me fix a prime p dividing n minus. In particular, from now on, n minus is not equal to 1. And let me let HP denote the p-adic upper half plane. Let me also let Tate be the Tate uniformization of E by CP star. All right. And to grossly simplify the p-adic uniformization theory that Henri was talking about this morning, let me state the following theorem. There's a canonical surjective map, which I'll call CD for Teretic-Drinfeld, from the p-adic upper half plane HP to the set of CP points of the Shimura curve xn plus n minus. Moreover, this map CD interacts nicely with the modular parametrization map in the following way. If we look at phi n plus n minus, evaluated on the degree 0 divisor, CD of t prime minus CD of tau, then this point on the elliptic curve is this multiplicative integral. You take this multiplicative integral, something in CP star, then you apply the Tate uniformization, and you get the image of the actual modular uniformization. The way you should think about this is the Tate uniformization and the multiplicative integral sort of give you the Abel-Jacobi map, the map uniformizing the Jacobian of this Shimura curve. Not only do we have this, but we can actually explicitly describe which points on the p-adic upper half plane HP correspond to the CM points on xn plus n minus. So we really know which tau prime and tau to take if you want to evaluate this uniformization map on a CM divisor. I won't make this too precise because I want to focus on actually how to compute this p-adic integral, which I think is clear now that this is the key thing that one has to do to be able to compute these Heegner points. So we need to show how to compute the multiplicative integral, which I'll call j of tau, tau prime, this multiplicative integral over p1 of qp of this rational function against the measure attached to E, where tau and tau prime correspond to CM points attached to some order O. And we can actually assume, by the way these points arise, we can actually assume that if we look at the reduction of tau and tau prime in P1 of Fp bar, we can assume that these things do not lie in P1 of Fp. Seems strange, but this will actually be very useful for us. All right. So this sort of, that's too early. So this sort of completes what I wanted to review of what Henri was talking about this morning and some things that John was talking about yesterday afternoon. And I'd like to launch into really how one would go about computing this p-adic integral, j of tau, tau primed, to high accuracy, so we can actually compute the corresponding Shimura-Heegner points. So let me roll this up for a minute to get some more Blackboard real estate. Where's the thing? Okay. All right. So we have this integral j of tau, tau prime, which we want to evaluate. So the first thing we can notice is that to compute the lights. To compute j of tau, tau prime, it suffices to compute for its Teichmuller representative and its p-adic logarithm. All right, the Teichmuller representative is no problem. You can get that just by doing a first-order approximation and just really computing the first-order Riemann sum. So you can do that in p multiplications. So this is no problem. What's a bit more subtle is computing the logarithm of j of tau, tau prime, just the standard branch of the p-adic logarithm letting log of p be 0. All right, so how do we do this? What I want to do is I want to break this up into a sum over the p residue disks of what I'll call log JA of tau prime. I think it's evident what I mean by this. I want to integrate over what I'll call B sub A, which is the ball around A of radius 1 over P. All right. Now, if we, for A equals 0 up to P minus 1, everything except for the ball at infinity, then we can really look at this. We can really split this up. We can write log of JA of tau prime as the log of JA of tau minus the log of JA of tau prime, where JA of tau is the multiplicative integral over BA of x minus tau d mu e. This is problematic in infinity because its integrand is a singularity. But at least for these, it's okay. And one can also treat the ball at infinity in the same way by translating the ball at infinity can be translated into the sort of finite part of P1 by just applying can be translated, say, to the PZP by just applying the matrix 0, minus 1, 1, 0. Now you have two ways of thinking about this. Either you can compute with two measures, mu e and this matrix acting on mu e, or if you're lucky, if you can work it so that your embedding of your quaternion order, the image of your quaternion order in the matrix ring includes this element. For example, you can always arrange this if you have the Hamilton quaternions. Then you only need to compute the one measure. So it works, and we weren't losing any generality by only working with this one measure mu e. Let me just put brushing this off to the side. All right. And now we can write, you can just do a Taylor expansion and write this as the sum over n of 1 over n times 1 over a minus tau of omega a n, where I define omega a n to be the nth moment of this measure mu e about the point A. How is that done exactly? Nope. Uh-oh. Well, the projector's off, right? Will it ever go back on? All right. And so this is just a Taylor expansion. You have to add and subtract A here to be able to use the usual Taylor expansion, but this is there's nothing really going on here. So to compute log of JA of tau to high accuracy, yeah. So to compute this to high accuracy, what you really have to do is compute these moments to high accuracy. To high accuracy, say, an accuracy of p to the minus m. I'm going to be measuring my accuracy p-adically, of course. So you would want to compute omega of a n mod p to the m for n goes from 0 up to m approximately, and a from 0 up to p minus 1. You need a bit more than m here because this n may have powers of p in it, but it won't have very many compared to this. So just let me ignore it and not put primes everywhere. All right, so this is the data we have to compute. Now again, we can't compute these moments just using Riemann sums because the number of balls increase exponentially as you increase your order of approximation by every degree. So we have to do this in some other way, and the way we do this is we're going to interpret this very data as the data specifying in a certain automorphic form with coefficients in a module of measures, or finite of approximations to measures. So this is what we'll do. We'll interpret this data as an automorphic form. And we'll compute this automorphic form using an iterative method. All right. So I'd like to describe now the, what mu e? Right. So so recall I stated the Jacquet-Langlands correspondence a little while ago. So this says that S2 of gamma naught of n, which is nu at n minus, this is isomorphic to S2 of gamma n minus. All right. Now, this, by what Henri was saying this morning, is isomorphic to the rigid analytic one forms on the p-adic upper half plane, HP, which are invariant by a group which I'll introduce in 5 minutes. So let me postpone the rest of the answer of this question. I brushed an intrinsic piece of notation under the rug when I stated the Tredde-Grinfeld theorem. So let me come back to this in a moment. Invariant under blank. All right. And of course, these will actually have interpretations as automorphic forms of the same type that I'm about to define. So let me talk for a moment about automorphic forms on definite quaternion algebras. I mentioned modular forms on indefinite quaternion algebras 20 minutes ago. Now let's look at their definite counterparts. So let me take B now as opposed to C, be the quaternion algebra over Q, ramified at n minus divided by P, and infinity. So I'm swapping P out of the ramification locus and I'm putting in infinity instead. So I have this thing compact at infinity. All right. Now, let me let R be an Eichler order of level P times n plus. So I swap P out of the ramification locus, swap infinity in its place, and move P over to the level. All right. Now, we can also fix an identification IP of B tensored out with QP with M2 of QP such that under this identification, IP sends R tensored with ZP to the usual 2 by 2 matrices with elements in bottom left-hand corner divisible by P. So fix this identification, and usually I won't even bother writing the IP if I'm considering an element of B tensor QP, which I'll always write BP as an element of M2 of QP. So this is, I'm going to sort of suppress the notation for this identification, probably unconsciously. All right. Oh, wait, now I can fill in this blank. The rigid analytic forms on HP invariant under IP of the norm 1 units in R of 1 over P. R star is a finite set, so to get a decent amount of units, you need to invert P. How do I work these boards? I don't know. All right. Let me let sigma denote the following semigroup of matrices. Really, I want it to be the stabilizer in GL2 of QP of the ball ZP in the p-adic in P1 of QP, together with enough matrices to give me a UP operator. That's what I want here. So really, I want the matrices that map ZP into itself by fractional linear transformations. You can just write this down as a set of matrices A, B, C, D in M2 of ZP, such that first of all P divides C, and A is in ZP star, and AD minus BC is not equal to 0. So this is some semigroup of matrices. Let me define the automorphic forms I want to consider. An automorphic form on B of level R, taking values in a right sigma module V is a function phi from BP star to V, invariant on the right by the global 1 over P units and by the center, such that I have a certain equivariance property with respect to the maximal compact corresponding to R. Note that this contains RP star, such that for every U in RP star, if we look at what I'll write phi slash U evaluated at B, which I define to be phi of left or right, phi of UB, U. So U acts on the argument and on the value, which I can because V is a sigma module and RP is contained in V, in sigma, such that this is equal to phi of B. So I want R of 1 over P star QP invariant functions on BP star which have this equivariance, this invariance property with respect to this compact. Now, this seems sort of strange because I'm defining automorphic forms locally at a certain prime, but this is really a global definition. One can define it adelically, and then strong approximation would bring you back to this local case. And it's just simpler to deal with a local description from the beginning. All right. And let me denote by S of V be the set of these forms. With coefficients in B. I'm suppressing the notation for the level because I'm never going to be changing it for the rest of the talk. Okay. And let me also remark that it's essentially for computational purposes that this is actually determined by a finite amount of data, assuming that we don't count elements of V as data. This is because if we look at the double coset space BP star mod R of 1 over P star QP star, modded out on the left by RP star, this is finite. Of course it is. You just look at it, right? No, actually, this comes from strong approximation, and this is identified with the class group with the set of left ideal classes of the order R, which can be shown to be finite. So if we take a set of double coset representatives, then this form is completely determined by its values on those double coset representatives. So for computational purposes, this is very, very useful. Yes, sorry. I find this overly challenging. No problem. Sorry about that. All right. Now, S of V is a set of automorphic forms. It's equipped with the action of a UP operator. In the way you would expect, phi slashed with UP is the sum where A goes from 0 to P minus 1 of phi slashed with 1 A 0 P. You can pick any double coset representatives for the appropriate double coset space there because of the action of sigma. And if V is a trivial sigma module, then we have a acting linear involution. Then we have phi slashing with WP. We can define this to be phi slashed with 0, 1, P, 0. All right. Now, this matrix is not in the semigroup sigma, so we can't really do this necessarily if there's an action on, what am I calling it? It's an action on V. All right. Now, sticking with the trivial action, in this case, these automorphic forms is the set of measures, is a set of measures. On P1 of QP, very much related to the comment I was making here about how these things, how we get one of these associated to an elliptic curve. Now, the way this works is, so let's, first of all, let me let B be the set of balls. In P1 of QP, and on this, we have GL2 of QP acting, and I've identified that with BP star. And the stabilizer of the ball ZP is exactly RP times the center. So what we have is we have B identified with BP star mod, on which side? Mod RP star, QP star. These are the, so we this is as a coset space. So a function on a function on B invariant under R1 over P star is exactly one of these automorphic forms. All right. And if we have that some automorphic form phi, which is actually an eigenform for UP and for WP, so if phi slashed with UP is minus phi slashed with WP is AP UP, where AP is plus or minus 1, what we'll get in this case when we have this form corresponding to an elliptic curve, then if we define a function mu phi on balls defined by mu phi, you measure the ball gamma ZP, where gamma is an element of BP star, measure it as follows. You take minus 1 as some sort of sign factor to the ord P of the determinant of IP of gamma, and then just multiply this by phi of B. Then this is a measure on P1 of QP, and it's of total measure 0. They're the same. No, I mean AP phi. Sorry about that. Thank you. All right. So these automorphic forms are really very closely related to these measures, which are very closely related to elliptic curves. So these are how these things come into the picture. Now, the technique for doing the integration that I'd like to do is to work in an even bigger space of automorphic forms. That actually, it's convenient to work in a bigger space because it gives us a little bit more room to maneuver, which will allow us to make some sort of approximation process that will converge to this form phi and allow us to compute its moments. I'll make this precise in a moment.
Actually, if we think about 3 toward 3 of B, then these are a locally constant function of this vertices of this tree.
Yeah. No, these are going to be the edges. If I didn't have any level structure, I'd get the. I have 2 degeneracy maps from that to the vertices. Yeah, these are going to be the maps on the edges of the tree. All right. So I want to define a fairly large space of coefficients for automorphic forms. And the definition is motivated by the fact that we don't need to be able to integrate every function. We just want to be able to compute moments of these measures mu attached to the elliptic curves. So I'm going to define functions that are essentially I'm going to define measures that are essentially characterized by their moments. So let me just let bold A be the set of convergent power series on the open unit disk in CP, which are defined over QP. I'll write it down. Yeah. It means that if you measure the whole space P1 of QP, it has measure 0. This is going to be a consequence of the fact that the Atkin-Lehner involution will send a ball to its complement. No, just the measure on the whole space. Yeah, these are certainly not positive. These measures take values in the p-adic numbers. Yeah. So this strange thing that really wouldn't happen in any sort of Archimedean context just happens naturally in this context. Sorry about that. Thank you. All right. So let's let V of x be this set of power series where an is in QP and an converges to 0 as n goes to infinity. These are some sort of analytic functions on a unit disk. And let me let, this is equipped with a soup norm. And let me let D be its continuous duals. So measures that are characterized by essentially by their moments, by their values on monomials. Now, this has a left action of sigma coming from the right action of sigma on the underlying set CP. So this dual has a right action of sigma, so it's a valid coefficient module for automorphic forms. So I want to consider the space of automorphic forms with values in D. And notice that we have a natural map, first of all, from D into QP, which I'll call pi 0. And this map is just total measure. Take a measure and then evaluate it on the whole space. It sends mu to mu of the constant function 1, or we can write this the integral over Zp of 1 d mu. So this map is just total measure. And this induces a map on automorphic forms, which I'll call pi 0 star, from S of D to S of QP. And this is where our form, say, phi sub E, corresponding to our elliptic curve and to the measure on our elliptic curve, lives. Now, it seems like this space may be far too big to be able to give any useful information about this. But when we restrict our attention to finite slope eigenspaces for UP in here, things become very tractable. So let me state the following. Oh, yeah. Yeah. So let me state the following proposition. Let phi in S of QP be a UP eigenform with eigenvalue AP equal plus or minus 1. It could be any p-adic unit. Let me restrict to this case because that's what comes up with from elliptic curves. Then there exists a unique UP eigenform phi in the set of automorphic forms with values in this module of distributions whose specialization under this map induced by total measure is the guy we started with. Such that pi 0 star of phi, a capital phi, is this little phi that we started with. So if we're talking about eigenforms with AP equal plus or minus 1, then there isn't anything more over here that isn't over here. So we have something of interest upstairs. But this thing is big enough that we can find some coarse approximation to this eigenform phi and then converge to it in a way that we can maintain, that we can increase the accuracy of it at each step. That's the idea that I'll try to explain. And this is, so we can give an iterative proof of this fact. Of course, we can't compute to infinite precision on a computer. What we really want is we want an approximation to this thing. Oh, one more. I forgot probably the most relevant point in this theorem. Moreover, this eigenlift phi satisfies the equality phi of 1 is equal to the measure associated to this form phi, if you restrict it to ZP. So, if we look at the form associated to our elliptic curve and the corresponding eigenlift upstairs, then we recover the corresponding measure on the elliptic curve, the thing we want to compute with, by evaluating at 1. And what I'd like to show in the little time I have left is how this lift really contains all the information we need to be able to compute these integrals. All right. So let's let phi e be the eigenlift of phi e, which is associated to our elliptic curve E. And we have the following proposition. If we look at the integral over a plus pzp of x minus a to the n d mu ex, this is exactly what I called omega of an, the thing we want to compute. This is equal to ap times p to the n times the integral over zp of x to the n d phi of 1a0p of x. So what happens is all this information here is stored as moments of various values of this big distribution valued automorphic form phi. You could also write this ap times p to the n times phi of 1a0p. This is a measure, and you evaluate this on the function x to the n. All right. So somehow this form contains everything we need. And note that we wanted this mod p to the n, mod p to the m. Right? We have a p to the n here. So we want this mod p to the m minus n. And this works perfectly because we actually have this cutting things off like this in this staircase form, cutting things off, higher moments off to lower powers of p, really actually defines sigma stable filtration on our set of distributions. So if we define Fn to be the set of all distributions mu in D, such that first of all mu of xn is in Zp for all n. I want to have some integrality condition here so I can approximate. And moreover, that mu of x to the n is in p to the, call this m to stay consistent, p to the n minus m Zp, then this is sigma stable. The sigma stable subgroup of D. So, in particular, we can look at the quotient. let me define an to be d0, where this 0 means things with integer moments, and let me mod out by this right state limit m. All right, let me mod out by that sigma state by that stable subgroup. This gives me a finite approximation module. So what we see is that if we look at then this really is the data I need to compute that integral that I looked at the beginning, j of tau, tau primed, modulo p to the n. And how is this done? Let me say this in one sentence. Well, there are a couple ways to do it. One, I'll say more about this tomorrow when we talk about conjectures we want to find other computations we want to do. But the way you do this and compute this phi n is you take any lift. Phi, say psi of phi e to s of an, any lift at all. Then what you have is that if you look at the UP operator or the AP UP operator and apply it to phi n times, you get what you want. And this, so if you can compute this lifting process, the action of UP you can also compute. If you can compute, then this can actually be carried out. So in n steps, you have the degree of accuracy you want. So that's how these computations go. I have a few examples, but I'm out of time, so I'll show it to anyone who wants to. Do I have 5 minutes? 2 minutes? Okay. Can I boot this thing up again, or did I do something weird to it? Okay. Oh, it's visible. Okay. Which one's the light orange? Okay. So if we look at this elliptic curve 38b2 in Cremona's tables, then the quaternion algebra which comes into the picture are Hamilton's quaternions. So if you want to, if we take a particular CM field generated by the root of minus 195, this CM field satisfies the appropriate Heegner hypothesis, and we can define a whole bunch of degree 0 divisors which arise from order 2 characters of the class group of this imaginary quadratic field, and one corresponding to the trivial character, which I have to cheat to get by applying some sort of degree 0 element of the Hecke algebra. And if I set pi equal to the image under the Tate uniformization of the corresponding multiplicative integrals over these degree 0 divisors, and carry out the process I tried to describe a moment or in the last half hour, then one can compute these 19 adic approximations, which can be recognized as these global points, which live in the Hilbert class field of Q of root minus 195. So this gives you a nice rank for Mordell A group. And I have another example where I look at an elliptic curve defined over the field Q of root 5. So this is an example not defined over Q. This is sort of nice. If I look at a certain CM field, F adjoin 2 times omega minus 15, where omega is 1 plus root 5 over 2, then this has class group of size 8 and a unique character of order 2. And if I want to find something in the isotypic component of the Mordell A group corresponding to that character, I define the appropriate degree 0 divisor, take the integral over that degree 0 divisor, try to recognize these things as global points, and you find these complicated points in higher degree number on elliptic curves defined over higher degree number fields. So it's sort of cool when you actually see the numbers working out. All right, I'll stop there.